All right. So the two theories that we just discussed on bonding that exist within molecules still have some ambiguities. What is much better understood and backed up by empirical evidence is how atomic orbitals are structured. Okay, so let's take a look. Let's start by looking at carbon. All right, now we already know from the periodic table that carbon has 4 valence electrons. Okay, it has 4 electrons in the second shell, and based on carbon's electron configuration, we would expect that 2 of those electrons would be in the 2s orbital, and then 2 electrons would be in 2 of the p orbitals. Okay, but when we look at carbon actually bonded to 4 different atoms. If you look at this picture, you can see carbon bonded to 4 different hydrogens. We see that all 4 of those bonds look identical. Okay, we don't have 2 shorter bonds representing the s orbital and 2 slightly longer ones representing the p orbitals. We've got 4 identical bonds. So what's happening? Okay, well, what happens is that the 4 electrons in the outermost shell, okay, again, the 2 shell, undergo something called hybridization, right? So for this to happen, one of the electrons from the 2s orbital needs to be excited. We need to give it a little bit of energy, and it gets bumped up to that empty p orbital, okay? Then we take all 4 of those orbitals, the 2s orbital, and the 3 individual 2p orbitals, and we hybridize them, okay? That is basically adding them together and averaging them, okay? This makes 4 equivalent orbitals, okay? Hybridization gives that carbon 4 of exactly the same orbitals that are completely symmetrical. Okay, these hybridized atomic orbitals are now degenerate, equal in energy, and they form 4 symmetrical bonds to hydrogen. Okay, again, when we use this word hybridize, what do we mean? We are essentially averaging together, right? In this case, we took 1 s orbital and 3 different p orbitals, added them up, and averaged them together. To denote this new orbital, we refer to these hybridized atomic orbitals as sp3 orbitals. There's a subscript of 3 by that p to indicate that we took 3 p orbitals as part of our hybridization. Okay. Now, since we did use more p orbitals than s orbitals, we're going to expect our average or hybridized orbital to resemble a p orbital a bit more than it does the s orbital. Okay, and we can see that that is true. We say that sp3 orbitals have like 75% p character because 3/4 of what was added to average the orbitals were p orbitals, and only 1/4 was an s orbital. Okay, and we can see when we look at the structure of carbon bonded to 4 different hydrogens that we do in fact have these orbitals that look exactly the same. And they are all completely symmetrical and resemble a p orbital a bit more than an s orbital. Okay. Now let's consider what happens when carbon is bonded to 3 other atoms, as is in the case that we're looking at here with ethene, or sometimes called ethylene. Okay, same name. In ethene, we have 2 carbons, which are identical in how they're bonded. Okay, you can see from the picture that each carbon has a double bond to the other carbon in the molecule and then 2 single bonds to hydrogen. So they're identical. Okay, since each carbon in ethene must bond to 3 other atoms, it only needs 3 hybridized atomic orbitals. Okay, so we take the s orbital. We're always going to use the s orbital in hybridization because we want to always start with the lowest energy orbital, okay? And since we only need a total of 3 hybridized orbitals, only 2 of the p orbitals and hybridize them. This gives us 3 orbitals that are equivalent. Okay. Now, since this time we used 1 s orbital and 2 p orbitals, we would refer to the 3 equivalent orbitals as sp2 orbitals because we only use 2 p orbitals. Okay. The carbon now has 1 remaining unchanged p orbital still on it. Okay. There's 1 we just left to live. Right. The shape of an sp2 orbital looks a little bit different from that sp3 orbital we saw. Okay, our sp2 orbital has a bit more s character. It's got 33% s character and only 67% p character. So it looks a little bit more like the s. Okay, remember, we only use 2 of the p orbitals. So we still have 1 unhybridized p orbital on the carbon, and you can see that in our picture below. That's the one that's still colored in. That's just an untouched y orbital. Okay. In the case of ethane, where we have 2 sp2 hybridized carbons bonded together, the sp2 atomic orbitals overlap with each other from each carbon to form a sigma bond. The remaining sp2 orbitals are bonded to hydrogen, which again only has 1 electron, so it's just got that 1s orbital. It can't be hybridized with only 1 electron. Now, the p orbitals on each carbon overlap to form a pi bond. Okay, that's producing that second bond that we see as the double bond in ethene. So in the double bond between the 2 carbons, we have 1 sigma bond and we have 1 pi bond. Okay, these terms are going to become important in the next set of slides we look like. Okay, we want to remember there's a difference between sigma bonds and pi bonds. The double bond has 1 sigma, 1 pi. Okay. Okay. The pi bond is formed by the overlapping p orbitals. Okay. And what is also interesting to note is that it is at a 90-degree angle from the rest of the molecule. A term we often use in chemistry is we say it's orthogonal to the molecule. Okay, lastly, let's look at ethine, okay, or acetylene. Here, we have 2 carbons that are bonded to only 2 other atoms. There's a triple bond between each of the carbons, and then the carbon has 1 bond to a hydrogen. Now, since ethine is only bonded to 2 atoms, we only require 2 hybridized orbitals. Again, we're always going to take that s orbital, and we're going to hybridize it with 1 p orbital. This will give us 2 exactly identical sp orbitals and then 2 untouched p orbitals. Okay. The sp hybridized atomic orbitals of each of the carbon overlap head-on to form that sigma bond, just like we saw in our last example, while the 2 unhybridized p orbitals overlap side by side to form the pi bonds. So for the triple bond between 2 carbons, we have 1 sigma bond and 2 pi bonds. All right, so let me ask you a question. Which do you think should be longer? An sp3-sp3 sigma bond or an sp-sp sigma bond overlap? Okay, well, again, sp3, we took 3 p orbitals. sp, we're only taking 1 p orbital. The s orbital is closer to that nucleus, okay? So sp3 bond lengths are the longest, okay, because it's got the most p character, and that p orbital is a little bit further away from the nuclei than the s orbital, okay? Then sp2, and finally the shortest are going to be the sp bonds, okay? And you can see this when we look at the actual length of a bond. sp bonds, shortest, then sp2, then sp3, okay? And what is also probably not going to come as much of a surprise is that triple bonds are not only shorter, but they're stronger than double bonds, which are stronger than single bonds. Okay.